Hello, I'm Lindsey Gray. I'm a scientist at Fermi National Accelerator Laboratory, and I've been working with Matthias Fey to bring graph convolutional operators to the PyTorch JIT. To frame the discussion about this, I'll first start with my field of research, which is high-energy particle physics, and give the problem context so we know why we're going after this and why we needed graph convolutional operators in the JIT. Then next, we'll talk about how we did it and how we make it deployable at scale. And then finally, we'll talk about some initial results and what's next for this project. In high-energy particle physics, we're facing a challenge of an assault of information in the coming years. Soon we'll be taking about an exabyte of data per year, of highly structured data with thousands of particles per event to identify and make use of. We've been looking into graph neural networks because they're very good at processing point clouds, which can describe a lot of our data. And we need to make sure that we can keep up with the compute demand that's coming from that, because there's been a trend in machine learning and high energy physics where we've been integrating machine learning deeper and deeper into how we do our science. So we really have to think carefully about how we use these models at scale and make sure that we aren't introducing any inefficiencies into the system that we propose to use. And this is where we get into wanting to use PyTorch and then wanting to use the PyTorch JIT for graph neural networks. So graph neural networks are neural networks that operate on structured data of arbitrary form. So you have the list of data, the xi that you see in this diagram to the left here, and then you have the relationships between those data, which are the arrows pointing between them. And a graph neural network can learn to make associations between each of those data using a neural network of some sort, and then gather and scatter all of that data between all the nodes over these associations between those data. And in PyTorch Geometric, it's very straightforward to write down what a graph neural net or what the pieces of a graph neural network are. So you can see here, this is an edge convolutional operator, and we're generating a message to pass with a multi-layer perceptron. We propagate, or the only thing we do in order to propagate the message and calculate the forward pass is just pass the messages. And the message that is generated is written down explicitly. So you can see that it's taking pairs of pieces of data and looking at the difference between two pieces of data as well as the local features of that data itself. And then you make a new message, pass it around, and try to classify the graph based off of that information. This means that PyTorch Geometric is really following the typical PyTorch principles, and it's quite straightforwardly Pythonic, experimentation-centric, and has a very clear API for writing these graph neural networks. And in addition to all of that, it is backed by well-performing code. On top of that, it's well adopted. It's got hundreds of citations for people doing experiments on graph neural networks and over 1,000 forks to date, with an active community of contributors behind that. And then, particularly, it's useful for high-energy physics reconstruction tasks, since most of our data can be described as point clouds, and we want to learn about the relationships between the points in those point clouds. On top of that, it's incredibly flexible, so you can define almost any graph convolutional operator that you can think of in PyTorch Geometric. And it does this by exploiting a number of features of Python that aren't available to the PyTorch JIT. So we needed to think about a way to get from the graph convolutional operators as they were in PyTorch Geometric to something that the JIT could use. The reason that we want to use the JIT is that it makes it incredibly simple to go from working on your models and experimenting on them to using your model in a trial and doing some first evaluations, and then finally deploying it at scale. And the JIT on paper is actually very suitable for graph neural networks because the JIT is able to capture very rich control flow, which is kind of the bread and butter of graph neural networks. And if we can get the JIT to synthesize a graph neural network, then we have this ease of deployment where we can go from experimenting on the model to all the way to deploying it at scale without needing to switch frameworks or change any of the models in substantial ways. And it makes it very, very easy to maintain the model, which is of vast importance if you want to if you want to work on a 3,000 person experiment. So how did we achieve this? We started off by using Python type hinting, and this was in order to stay as Pythonic as possible while making the inputs and outputs of the operators more concrete so they could be statically analyzed by the JIT and compiled down. In order to get there, we do a simple static analysis on what the user provides. So we dynamically rewrite the user code when they ask for a JITable version of their module, and maintain exactly the operations that they expect whilst doing this. And then we made sure that there are minimal code changes to the model in order to make it something that you can deploy through the JIT. And in particular, once you have a convolutional operator ready to go, all you have to do is type .jitable, and that model can be interpreted by the PyTorch JIT. So what does this look like in terms of changing a PyTorch geometric operator and to make it JITable? Essentially, we have to obey all the rules and then do a little bit of dynamic rewriting underneath. So what you can see right here is that we've type hinted every single variable that's going in and coming out of this particular convolutional operator. And we've also added an additional propagate type hint that tells the JIT exactly what sort of data is being passed in and out of the propagate function, which is determined dynamically inside of PyTorch Geometric's message passing class. And that's just the user interface that you see when you're trying to write something. So how did we do it? The first thing that needed to be done, that Matthias worked extensively on, was making a campaign or performing a campaign to get all the custom ops into JITable form. So Torch Geometric uses a huge number of sparse operations and quite a number of clustering algorithms as well, and all of those needed to be made available. And then finally, let's talk about this static analysis that we do. So we go and look at all of the functions that are in a user's graph convolutional operator, and we make a concrete version of all of the variables that are being used in those functions so that we know the types ahead of time. And then we rebuild the class such that it uses these known ahead of time definitions, and turn it into a class that uses those definitions by default instead of having to infer them during execution. So by doing this quick rewrap of the class, we're able to turn or take the exact same class and turn it into something that's JITable and usable at scale. So one example of this from high energy physics is that we are looking at imaging calorimetry, and what you see here in the plot to the left are a whole bunch of energy deposits inside of effectively a giant 3D camera. And each one of these different colors that you see is not known until we run our reconstruction algorithms on all of those input points. And now, instead of having to write a reconstruction algorithm by hand, we can train a graph neural network, compile it down into JIT code, deploy it on NVIDIA Triton, pass off our data into an inference as a service engine, and then bring back all the cluster assignments as executed on GPU, and then go on about our business of doing physics with the outputs. And this is really cool because we didn't need to add PyTorch to our experiment framework, which is already a couple million lines of code and then a large number of dependencies as well. And we also didn't need to add CUDA or maintain it. So this is a significant ease of operation for us, whilst also getting these powerful algorithms inside of CMSSW so we can use them. So we have seamless GPU integration through inference as a service, and the typical 100x speedups that you expect. And we also get this factorized software stack that really eases our maintenance for the foreseeable future when trying to use these operators. So in conclusion, you can see that GNNs are becoming more widely used tools, and we have a vast amount of point cloud data that we want to assess the relationships between all those data. And we've been looking into GNNs with PyTorch, and it's widely accessible via PyTorch Geometric. We needed a way to make these models deployable at scale in a very easy way that didn't incur anything cumbersome in terms of maintenance burden. And the PyTorch JIT is one way towards that. And as it was before, GNNs were really difficult to deploy, so we wrote extensions to PyTorch Geometric that make this transition almost seamless. And you can check out that example if you follow the link in the slides. All of the currently implemented convolutional operators are there, and it's very easy to add more. So we can really cover all of the literature for GNNs already out of the box and make them deployable at scale. We've tested this in inference as a service tools like NVIDIA Triton to make the GNN deployable and easy, or the serialized GNN easy to scale. We only had to add one additional container layer on top of NVIDIA Triton in order to make this work. And this gives us scalable event processing on GPUs that's factorized from our typical compute, which is good for us. So the next steps are to move from this proof of concept that I showed you into something that can really be battle tested that does exactly what we want. Because that wasn't the whole story that I showed you. In particular, in high energy physics, we infer on thousands of times more events than we train on. So we really have to make sure that we have a robust algorithm. And then we also need to make sure that it can scale because we have to run this on tens of thousands of workers. So really understanding the scaling behavior is key to our success. And that kind of feedback can also help PyTorch and Triton grow. On top of that, we're going to start adopting more models into the inference as a service architecture, since it eases maintenance burden and very straightforwardly exposes GPU as accessible compute for our processing systems. And then finally, we want to optimize the execution of these high energy physics reconstruction machine learning models. And we're really only at the beginning of building the first efficacious models for this. And we have to now take our time experimenting on those models, working with the JIT, working with the structure of the models themselves and how we're presenting the data in order to get what we really want in the end. And that means that there's a ton of really exciting developments ahead of us for using cutting-edge machine learning for fundamental science. Thank you.